Okay, here is my video assignment for video assignment number 1, chapter 10. We have our unknown unit cell. I've written down all the information that is given, and I've written down an equation for what is given. FeXOY plus CO transfers to Fe plus CO2. We don't know the formula of our oxide yet. That's what we're trying to figure out. With the information that is given, we can use the equation PV equals nRT, the ideal gas law, because we are given all the variables except one, to find the number of moles of FeXO, or number of moles of CO2. Now, it's important to find the moles of CO2 because it is proportional to the amount of oxygen in the whole system, because 1 mole has to come from here, 1 mole has to come from here, equals our 2 moles here. We can't have half number ratios, so we know that CO2 is proportional to the amount of oxygen in the whole system. Therefore, we need to rearrange our PV equals nRT, which gets rearranged to N equals PV over RT. When we plug in our numbers, we have atmospheres here, because millimeters of mercury will not cancel out with the units we're using. So we need to do the conversion factor of 751 millimeters of mercury. Using 760 millimeters of mercury equals 1 atmosphere, which gets us into 0.998 atmospheres. That is where this number comes from. This number is explicitly told to us. This number is a constant, and we need to use this specific one because it is in atmospheres per liter. That cancels the atmospheres, cancels the liters, and then Kelvin. That equals our number of mole of CO2, which is 0.0496 moles. That is, again, proportional to oxygen. So when we come down here, we can say 0.0496 moles of oxygen. Then we can take the molar mass of oxygen and use that to find our grams of oxygen, which is 0.733 grams of oxygen. Now, we know that the total grams of our iron oxide is 2.66. We know that we have 0.733 of those grams are oxygen. Therefore, we can take 2.66 grams of the iron oxide minus the amount of oxygen in it, which is 0.733, and that equals answer A, 1.93 grams of iron in the oxide. Now, we are going to do a molar ratio because we're doing an empirical formula. And in order to get an empirical formula, one way to do that is through a molar ratio, which is the way I'm choosing to do that. Iron has a molar mass of 55.85 grams per mole on the periodic table. Using that as a conversion factor gets us to 0.0344 moles of iron. Then we pull the moles of oxygen from here and the moles of iron from here, which gets us to this. When you do that calculation, you get a molar ratio of 1.3, which essentially means since oxygen is on top and iron is on bottom, we have 1.3 moles of oxygen to every 1 mole of iron. I picked the number 3 to multiply those two to get them to a whole number because it's what worked. I trial and errored, and 3 is what worked. This got me to approximately 3.99, which is approximately 4 molecules of O. I did the 1 times the 3 for the iron because we have 1 mole to 1.3 times 3 is the whole number I'm deciding to times it by, equals 3 moles of iron. That gets us the answer to question B. Our iron oxide has a composition of Fe3O4. Now, we need to figure out the last part, which is how many atoms of iron and oxygen are in our theoretical unit cell. In order to do that, we need to find the molar mass of the Fe3O4. I wrote this down wrong. In order to do that, we take our 55.85, which is the molar mass of iron, times 3, because that's how many iron atoms are in the oxide, gets us 167.55. We do the similar thing for oxygen. Molar mass, amount in the oxide, gets us 63.96. You add those together to get us the total grams, the molar mass of the iron oxide. That will become important later. The other piece of given information that I did not write down over there is that one side length is equal to 839 picometers. This is going to give us our volume. From here, we convert picometers into centimeters using 10 to the negative 10th. And then in order to get the volume of a cube